And we're going to move on to the next talk, which is by Rachana Bhatawdekar. So Rachana, if you want to get your slides set up.
Yeah. Okay, can you see them?
Yeah, we can just, now it's good.
Okay.
Take it away, Rachana.
Can you also see my video, because I can't see myself anymore?
I can see.
Okay, that's fine then. Okay, great. So, hi everyone. My name is Rachana. I am a research fellow at ESTEC in the Netherlands. And in this very short talk today, I'm just basically just going to touch upon the motivation behind studying the faintest galaxies in the epoch of reionization. So, essentially, how we can study them, why we should study them, and how we can study them with current facilities before the launch of JWST. And finally, share some of our latest results that recently got published in AbJ. So starting with the very familiar schematic that shows the evolution of the universe, we know that epoch of reionization is an important phase change in the history of our universe. And we also know that this phase change must have started as early as redshift 20 and ended at about redshift 6 or so. But what we don't know is what these first energetic sources responsible for reionization are. Are they galaxies, are they quasars, are they epoch 3 stars? And we also don't know when exactly they formed. And soon, JWST will help us answer these very fundamental questions by looking for the first light objects in the redshift range of 10 to 15. But with HST, we have been able to discover galaxies up to redshift 11 well into the epoch of reionization. So if we look at the literature, one can see that there have been several studies with HST that basically suggest that early star-forming galaxies could well be the best candidates to drive reionization. So, for example, if you look at the luminosity function studied by Finkelstein et al. And Bowens et al. Out to redshift 8 and 10, you will see that it revealed a very steep faint slope at these redshifts, which essentially means that there is a significant contribution from the faint galaxies. And also, if we look at, for example, the stellar mass function studied by Song et al., it also shows that the mass function evolves with time, and it actually becomes steeper with higher redshift, such that there are more low mass galaxies at high redshift than at low redshift. And so the implication of these studies essentially is that the UV luminosity density responsible for reionization is dominated by faint galaxies. But the challenge, of course, is that these faint galaxies are beyond the detection limits of HST. And so if this idea of galaxy-powered reionization has to work, we need to integrate the luminosity function to an absolute magnitude of around -13. But another problem is that simulations actually predict a turnover in luminosity function at some magnitudes greater than -17. So should this happen, firstly, it will present a challenge for our models of reionization. And secondly, this turnover, if it exists, it lies beyond the reach of HST. As I said before, finding these distant galaxies will be a routine with JWST, but until then, the only way we can address this problem is by combining HST with lensing of massive clusters. And so for this very reason, the Hubble Frontier Fields program was designed, in which Hubble observed these 6 massive clusters of galaxies as gravitational lenses, along with 6 adjacent parallel blank fields. But the problem with galaxy clusters, of course, is that these clusters are also home to these massive and bright foreground galaxies, which actually makes it extremely hard to see the faint objects. And so to solve this problem, we developed a technique that accurately removes the most massive foreground galaxies from the critical lines of the clusters, because that's where the greatest magnification of distant objects occur. And it's an iterative process, and we remove these massive galaxies using Galapagos and Galfit. Unfortunately, I don't have enough time to go into the technical details of it, but the method is explained in detail in our 2019 paper, in case you are interested. But as an example, on the left is MAX 0416 cluster, on which the subtraction procedure was applied. In the middle is the Galfit model of the galaxies, which were subtracted from the cluster. And on the right is the final subtracted image, in which you can see some of the faint sources that were basically hiding behind these galaxies. And so with this method combined with lensing, we were able to derive the very first stellar mass function for Frontier Fields program from redshift 6 to redshift 9. We used the SCD fitting method using imaging from HST, VLD, and Spitzer to estimate robust stellar masses of our IZ sample, demagnified them using all the available lensing models for Frontier Fields. And then we fit a Schechter function to the data, which is shown by the solid green line here in these plots. A key result of this paper is that we were able to characterize the mass function to the lowest measured stellar masses for the first time in Frontier Fields, 10 to the 6.8 solar mass. And our results also showed an apparent steepening of low mass end slope with increasing redshifts from minus 1.98 at redshift 6 to minus 2.38 at redshift 9. These slopes are steeper than previous studies. And as you can see, we are also not finding any evidence of a mass function turnover in the mass range probed. Recently, Furtak et al. Have observed a turnover in their study, which is shown by these red points here in this plot. But the turnover primarily is because they derive their mass function by convolving their m star MUV relation with the luminosity functions of ETEC et al., who do find a turnover in their luminosity functions, as I will show in the next slide. And so with the same sample, we also derived the luminosity function, and we were able to characterize it to magnitudes as faint as minus 13.5. The faint slopes of our luminosity function also showed an apparent steepening with increasing redshift. And once again, we did not find any evidence of a turnover that some studies like Bhuvan et al. And ETEC et al. Have found at an absolute magnitude of around minus 15, which is shown by these yellow and black points here in this plot. And so with our new measurements, we also estimated the UV luminosity density and stellar mass density. As you can see in this plot, these orange circles, which represent the luminosity density, which we have estimated by integrating our luminosity functions to an absolute magnitude of minus 13.5, which is the faintest galaxy in our sample. They are quite high compared to the luminosity density estimated by with magnitudes of minus 17, which is the observational limit of HST. And they also show a smooth decline towards higher redshifts in both the cases. Then if you look at the plot of stellar mass density as a function of redshift, what we find is that not only the stellar mass density has increased by a factor of 15 from redshift 9 to redshift 6, but there is also a surprisingly high amount of stellar mass density for galaxies in the early universe up to redshift 9. And this basically is an indication that galaxies of masses around 10 to the 8 have already formed a significant density by this time. And so what this tells us is that the star formation and assembly history of galaxies is significant in the epochs of redshift greater than 9, which we cannot probe in detail until the launch of JWST. And then very recently, we also looked at the UV colors or UV spectral slope beta of our same sample of galaxies. Once again, we estimated the UV colors using a SCD fitting method. And in this plot, we are first looking at the correlation between rest-frame UV and beta by plotting median values of beta in 3 different bins, which is shown by these black points here in this plot. This correlation has also been looked into by several other studies. For example, Bhuvan et al., these sand points here in these plots, they found the correlation between rest-frame UV and beta such that faint galaxies have bluer UV slopes. But then there are also other studies, for example, from Finkelstein and Dunlop, who do not find such correlation. But again, these studies are limited to an absolute magnitude of minus 17, which is shown by these dashed blue lines here in these plots. And so with Frontier Fields, we are for the first time able to look at the UV colors of galaxies between minus 17 and minus 13. And the reason this is particularly exciting is because models actually predict that values of beta equals minus 3 do not appear until magnitudes greater than minus 17. So should we detect such blue slopes from these galaxies, we will potentially discover the very first evidence for very low metallicity star formation in the early universe. But as you can see from these black points here in this plot, we are not finding any correlation at all redshifts we study. But interestingly, when we look at beta as a function of redshift, what we find is that these median values of beta, these orange circles, they appear to evolve mildly from redshift 6 to redshift 9, such that galaxies have lower values of beta at high redshift. And this blue dotted line over here, it basically shows the UV colors. It suggests the expected colors if galaxies had stars with very little metals. And so our results basically show that the UV colors of galaxies with frontier fields are not blue enough to have stars with very low metallicities. And only JWST will be able to provide a clear picture of this. But as of yet, there is no evidence for exotic or POP3 stellar populations at the highest redshift scope with frontier fields. And finally, as I showed earlier, we do not find any correlation between rest from UV and beta, but we do observe a strong correlation between beta and stellar mass, such that lower mass galaxies have bluer UV slopes at all redshifts. This paper recently got published in ABJ, in case you are interested in having a look at these results in detail. But yeah, with that note, I'll just summarize my talk by saying that we have been able to characterize the mass function to very low masses for the first time in frontier fields. And we have also been able to characterize the luminosity function to magnitudes as faintest minus 13.5. Then we have also observed an apparent steepening of faint end slope and as well as low mass end slope with increasing redshifts. But in the same cosmic time interval, we have found a lack of evidence of exotic or POP3 stellar populations. And so these results basically do support the idea that faint low mass galaxies in the early universe could have been responsible for reionization. And they also clearly show the potential science that can be done with JWST, which will provide a clear picture of whether there exists any turnover in luminosity function and mass function, and also on the presence of POP3 stars.
Thank you very much, Rachana.
Yeah, thank you.
Thank you. Thanks again. And yeah, if you want to ask Rachana a question, you can please put that in the Slack channel for 4A. We'll just wait a few seconds for questions to come in.
Right, so got the first question. So how robust are your steeper luminosity function slopes without contamination, the length model, uncertainties, etc.?
Sorry, Masami, can you repeat that?
How robust are your steeper luminosity function slopes? Okay, length model, uncertainties, etc.
Yeah, so basically, if I go back to the plot, okay, I can't share my screen for some reason, but the error bars basically in the luminosity function, estimation of luminosity function and mass function, we have accounted the photometric errors, the errors due to stellar masses and luminosities, and also lensing maps. We do have certainly included all these uncertainties while estimating these.
Thank you, Rachana. So I think in the interest of time, we're going to have to move on to our next talk. But if people want to continue asking questions, please do so in Slack.